Okay, let's look at the section 10.1. This section talks about the numerically equivalent sets, right? Let's look at the definition, right? So notation is cardinality of A is equal to cardinality of B. When the cardinality are the same, we say numerically equivalent, but here's the precise definition. We say cardinality of A is equal to cardinality of B if there exists a bijective function f from A to B, right? So another way to say is that we can say set A and set B are numerically equivalent, right? Which just means that they have the same cardinality, right? So for example, if you have a finite set, so you have a set with 1, 2, 3, right? This guy is numerically equivalent to set with the same number of elements, so say A, B, C, right? Also, if you have a say set of natural numbers, so say set of natural numbers, right? This is numerically equivalent to, all right, set of all positive even numbers, say 2, 3, 4, 6, 8, and so on, right? You can easily come up with bijection from a set of natural numbers to a set of positive even numbers by having a function like f of x, or maybe I should say f of n, is equal to 2 times n for all n in the set of natural numbers. You can double check that this is actually a bijection, or one-to-one and onto, but this is a bijection. So these two guys have the same cardinality. All right, let's look at the theorem right here. All right, it says that the S is a collection of non-empty sets. So S has a bunch of non-empty set. We can define a relation saying that the two sets are related to each other. Maybe I should say A is related to B, that if they have the same cardinality or they are numerically equivalent. Say it's that this relation is actually an equivalence relation, right? So basically what we're saying is that numerical equivalence is equivalence relation, right? So let's double check. All right, so we pick any set A from this collection of non-empty set S, right? We know that the identity function, there exists the identity function on A, right? This guy is bijective. Bijective, right? Which means that their A is numerically equivalent to itself, right? So which means that A is related to itself by this relation R, right? So this tells you that this is reflexive. All right, let's look at the symmetry. All right, so let's say if A is related to B by this relation, right? which means that you know, A and B are numerically equivalent, so there must be bijective I can't spell bijective, so bijective function f from A to B. So that's by definition, right? But if you have a bijective function, you can find the inverse function. So there exists the inverse function f inverse, which goes from B back to A, right? And we know that if you have a bijection, inverse is also a bijection. So is also bijective, right? So which means that B is related back to A by this relation, right? This this tells you that it is symmetric, right? And transitivity, so we assume that the set A is related to B and the set B is related to C by this relation, right? Which means that there exists which means that there exists a bijective function say f from A to B, and also there exists a bijective function, let's call it G, from B to C, right? Then we can compose these two bijective functions to create another bijective function. So we can say G of f, right, is a bijective function from A to C, right? Right, so we found a bijection from A to C because the composition of bijective function is also bijective, right? So this tells you that A is related to C, right, which establishes the transitivity, right? So you can see that numerical equivalence is an equivalence relation. So we may assume these three properties, right? That's it. I hope that this was clear.